Okay. Whatever. Okay. Yeah. So like I said on Slack, today we're going to talk about the K framework. Give a demo of defining a programming language using K and adding a bunch of random features to it. So the language is going to be sort of a Python-ish language, in that it'll be sort of a dynamically typed imperative-E language. So I'm going to call it Snake because I tried to find a cool Snake name and then I was like, that's okay. Snake is fine. Anyway, so if you have K, you should make a file called snake.k, and that's where we're grading all the code. And if you don't, then you can watch or whatever. Yeah, so the first goal, I guess, is here's an example program in this language. And what it does is it calculates the nth Fibonacci number, just using a standard loop approach. And yeah, so we're gonna try and get this program working, and then we'll add more things so that we can use for loops and functions and all the stuff that you would expect from a real programming language. Okay, so first thing we need to do is define syntax. So we're going to need to have these assignment statements and while loops and comparison and addition and variables and yeah, all that. So let's see. So the way we do this in K is we start by saying syntax, and then you give the category, they're called sorts actually, of, you give the sort various rules that say which things are, in this case, values. So we want ints and booleans to be values. By both of these are predefined. They come from this library that I'm importing. It's basically just like the standard library of K. It defines things like integers and booleans and lists and sets and all that. We're going to use it because that's much easier. And then on the right, I just have this thing set up that will compile whenever I make a change to the files. So yeah, right now it doesn't parse because I don't have enough things defined, but that's fine.
So, can I ask a question?
Yeah, sure, please.
Yeah, so I noticed the syntax looks really similar to like EBNF.
Yes.
Does it like diverge somehow, or how does it work? And it's just, is this just for the parsing step, right?
Yeah, this is just for the parsing step. Yeah, so it's made to look like EBNF. It's basically the same, except that there's like attributes you can put on the side, which we'll get to in a minute. But yeah, it's basically just that.
Okay.
Let's see. Yeah, if you have questions at any point, just stop me and ask. I should have the chat open so I can see if there's any questions there. Wait, can you guys see that chat window? I can never remember if you guys can see this.
I see a gray rectangle.
Okay. Well, I'll just open it every now and then to check. Anyway, so we have values and we have expressions, and the difference being that expressions are things that will be evaluated to values, and values are already done evaluating. But values are also expressions, in that this just makes writing like your program's easier because you don't have to say like value or expression, value or expression, value or expression. You just say expression. So yeah, so expressions can be values, and then we take a look at our program. The other things we need is variables, comparison, and addition. So variables, again, this is a built-in thing. It's called ID. Basically, it's your standard programming language variable names, capital letters, lowercase letters, underscores, numbers, but not at the beginning. Yeah, and then the other things we need addition of expressions and less than with expressions. We could add more things too, but I will just stick with this for now. Yeah, so that's all we need for expressions. And then for statements, we need to have assignment. So ID equals expression. And then we also need, what's the other thing? Oh yeah, while loops. So while expression, and then some statements, which I haven't defined yet, but we want to be able to have more than one statement in the body of the while loop. So let me define statements. Statements is either one statement or a concatenation of two lists of statements. And yeah, so the reason why I do it like this is because it makes it easier to write the language definition later, because I don't have to have it always starting with a statement. I can concatenate them more easily. But this does introduce parsing ambiguities because of the associativity. For example, if I have like these four statements, it's not clear whether it's, you know, x equals 0 followed by all of these things, or if it's like x equals 0, y equals 0, then all the next things. So it could be parenthesized like this, which would be weird, but that could be, or it could be the more, you know, sensible thing where it's parenthesized like this. So to resolve this, I'm just going to say that this concatenation thing is associates to the right, which will give me what I want. And that the first thing will be a statement, and then there'll be more statements.
Is there a reason you made it a concatenation of two statements instead of just statement and then a statement?
Yeah. So because later when I'm writing this, I'm going to want to rewrite things that are not so. Yeah, I'm going to want to rewrite things into different like lists of statements. And sometimes I want to concatenate a whole list of statements to another list of statements instead of adding those statements one at a time. And this is just more convenient for that. Yeah.
Okay, makes sense.
Yeah. And now, okay, yeah. So here's the latest run, and we can see that it has successfully parsed our program. It looks kind of gross, but you know, it's all good. Program doesn't do anything, but now we can parse the program. Which now means we need to start actually adding behavior to our language. So the first thing to do is we have these this huge list of statements, and we want to process each statement one at a time. So to do this, I'm going to take this huge list of statements. So I have one statement followed by other statements. And I want to split this up into statement followed by other statements. So this funny arrow thing here is the built-in sequencing operator in K. And all it means is evaluate this thing until it's done, then evaluate this thing until it's done. And yeah, and so the way to write a thing that is done is just a dot, which is kind of hard to see, but you'll see what I mean in a minute. Okay, so now over here, we can see in the most recent run of our program, what it did is it took this first statement off and said, we're going to start evaluating x equals 0 now, and then evaluate all the other stuff, which is great. But now we need to actually evaluate x equals 0. And to do that, we need some concept of an environment that holds all the current values for each variable. Actually, let me check the chat for questions. Yes, you should follow the Linux commands if you're on Mac. That should work. Except you won't be able to install the dependencies with them, but you can use Homebrew or something probably. Okay. Let's see. Yeah, so we need to have an environment. So in K, the way you do this is you create a configuration. So right now, there's actually a default configuration, which just has this one cell, is what it's called, the K cell, which holds the program that we're currently executing. And we need to have the K cell. This is just a special value that says, like, whatever the program is that we parsed, put it in this cell. This is going to be a list of statements. And then the other thing in the configuration we need an environment, which is going to be a map. So the environment will map variable names to variable values. And .map just means empty map. So if I do that, When it runs, I mean, everything will be the same, but you'll also be able to see the actual environment that we have. Yeah, so also a quick comment about the backends and how K works is, so you write these K files and then you compile them using their incredibly cleverly named compile command. And there's a number of different backends you can pick from. So there's the Java one, there's an LVM one, there's a Haskell one. Basically, there's the difference is that the Java backend and the Haskell backend are symbolic. So you can do more interesting things, like you can sort of introduce new variables and use like variable unification to define things, which is convenient sometimes. I'm not going to do it today, but I just prefer working these symbolic backends more because they work more like you would expect mathematically. But they're also slower. So if you want it, I mean, if you're concerned about speed, you should use like the LVM backend or something. If you're really concerned about speed, you should handwrite your interpreter. But if you're concerned about speed of development, you should use K. Anyway, yeah, so now we have our K cell and we have the environment cell, which has nothing in it, but that will change shortly. Okay, so to process an assignment, what we want to do is we want to say, when we're doing something like x equals v for some value, what we want to do is in the environment, oops, yeah, well, yeah, so when the K cell looks like this, so it starts with x equals value and then there's other stuff. What we want to do is in the environment, we want to take the current environment and give x whatever value is on the right-hand side of the assignment. And then after we do that, we are done evaluating this statement. So we rewrite it into dot, which means done. So if we write this now, it will compile and then run the program and we'll be able to process all the assignments. Or at least if I didn't make any mistakes.
What is the dot dot dot?
Dot 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 just means, yeah, so here like the K cell starts out with x equals 0 and then there's all this junk. Dot 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 just means whatever stuff is after this part that I specified, I don't care about and just don't change it.
Oh, I see, okay.
Yeah. Let's see, yeah, so now when we run our program, we get an environment with all the variable values that we set, and then we don't know how to vary while loops, so that's still there, but we'll get to that shortly. Okay, so while loops. Actually, maybe I should stop. Are there any other questions before I move on? Okay, well, I'll check the chat. Okay, yeah, so there's lots of ways you could define while loops. The way we're going to do it is sort of, well, I don't want to say clever, but clever way. So we're going to need to define if statements to make this particular definition work, but we want if statements in our language anyway, so it's not a big deal. So we're going to do it is we're going to define it as if condition, then we run the body of the loop. Whoops, it's going to yell at me, but anyway, we run the body of the loop and then we run the while again, or we check the condition again and basically just recursively expand like this until the condition is false. And then when the condition is false, we will do nothing, which I'm going to call skip. I guess we'd call it pass if we wanted to be more like Python, but whatever. Skip is more typical in programming language stuff. Okay, so to make this work, of course, we need if statements. So it's very similar to the whiles. We have if expression, then the branch when it's true, and then else, the branch when it's false. And if we do this, and define skip, then our program will now expand out the while loop, but not know how to handle the if yet. Or it should. Actually, I think it will need, one sec. Yeah, one sec. Okay. Yeah, it was compiling an old definition. Anyway, so to evaluate if statements, we're going to take advantage of K's built-in sort of evaluation mechanisms, where we say basically which expressions we need to evaluate before we run, before we evaluate the larger statements. So for example, in an if statement, what we want is just kind of obnoxious. We want to say that it's strict in the first argument. And what that means is we evaluate expression until it's a value or until it's a result, which we'll define it as to be just a value. And then once that's fully evaluated, then we evaluate the if statement. And to make this work, we need to tell K what our values are. And for us, for the moment, it's just val. So we just need to, yeah, so K result equals val tells it that, one sec, tells it that expressions should be evaluated until they become a value. So in this case, an integer or a bool. Again. Okay, and yeah, so you can see that when we start evaluating this if statement, we're going to need to know what it means to, for two numbers to be less than each other. But actually before that, we need to know what it means or how to look up a variable in our environment. And yeah, so I'm going to go ahead and make other things strict. So both of these operators should be strict, which means we evaluate the left part and right part of the addition and the left part and the right part of the comparison before we evaluate the whole addition or comparison. And then we also want to do the same thing for assignments. It'd be strict only in the second argument. So this expression here, not in this ID, because we don't want to evaluate like x equals 10 to be like 0 equals 10 or something, because that would be silly. Anyway, yeah. And now we are at a stage where the next thing we need to evaluate is a variable n. So what we need to do is tell K how we want variable lookup to work in our language, which is quite simple because we just have this very simple environment. And the way we do it is rule K. So when x is a variable, this will evaluate to v, where v is the thing that x maps to in the environment. So what this means, the triple dots is essentially just like before. A map is basically like a set of these key value like mappings. And I'm just saying that somewhere in this set of key value mappings, there's one that looks like x maps to v, and that's the one that v comes from. So the other way you could write this is env, just give it a name, and then I could say env of x if I wanted to. But I like this style more, and this is the one that people typically use, so I'll use this one. Anyway, so now we can see in our evaluated code that the next thing we need to define is when one number is less than another number. So this is built into K. I mean, you could define it yourself, but this is built into K, so we're just going to use what K defines, saying that I1 is less than I2 when I1 is less than int I2, which is, like I said, the built-in integer inequality. And then we'll do the same thing for addition, I1 plus int I2. And if we rerun this again, we'll make it a bit farther before we get stuck. Yeah, let me see. Actually, what else do we even need? Oh, we need skip. Yeah, but other than skip, it should all work. So oh, whoops. I also need to define the if statements. Okay, yeah, so we fully evaluated the condition of the if statement, but we need to tell it what if statements actually do first. So let's see, where should I put this? Let's put it here. So rule if true. You have some statements here, else something else, but we don't care because the condition is true. Then we evaluate to A, and if false, else something here, we evaluate to B because the condition is false. Okay, and that will give us evaluation of the if statements, and then I think the last thing we need is skip before our little example works. And skip is very easy because skip does nothing. So to do skip, all we have to do is rule skip goes to dot. Remember that dot means done, and that's all you need to do skip. You could do without skip and make the statements list possibly empty if you wanted, but that's, well, I prefer this approach. So yeah, that should be, why is it not like that?
I think I got most of it. I'm just confused about the first rule first. I'm confused as to what exactly it's doing.
This one?
Yeah.
Yeah. So it's taking a list of statements and breaking off like one statement at a time from the front.
Oh, so it's like a cons operator.
Yeah. Yeah, just the cons is just like space.
I see. Okay.
Yeah, because I defined it like this. If I wanted to make it like something else, I could put like a semicolon there or something, and then it would be semicolon here is like the cons.
I see. Wait, but in your definition, you use statements, and this one is using statements. So, it's because statements can also be defined as a statement. Yeah. I see.
Okay. Yeah. Although actually, this is not breaking apart correctly. One sec. Let me go check my secret notes file. Oh, I have it differently.
Are we able to get these files later, or?
Yeah, I'll post them on the.
Okay. And also, what is like K mainly used for?
K is mainly used for, like, you did like define a model of a programming language, and then you can use K to do like verification stuff. So one of the things that the people who made K did is they have a Ethereum like virtual machine implementation in K, and then they can use it to like verify smart contracts and stuff. And they also have a C definition, which they can use to find undefined behavior. And you can also do things with multi-threading, like search the whole possible space of like interleavings of threads and see if there's any race conditions. Mm-hmm. And you can also just define programming languages. But yeah, typically what people do is they define a language and then use the definition to find, to do verification stuff. Does that answer your question?
Yeah.
Okay, cool. What was I doing? Oh yeah, I have this. Yeah, I'm not sure why it's not breaking it apart like I want, but I can use my other definition for my file. It should be associating everything to the right, but I guess it's not. Well, I don't know. I'm not going to spend a lot of time debugging it, I guess, because I know that this will work. I'll look into it later. Yeah. Anyway. Yeah, so once we do this, we should have this program working at least. And did I write the program wrong? Because it ran, but I have the wrong numbers. Let's see, t equals x equals y equals t plus y equals I plus 1. Oh, because starting them both off at 0. Yes. Okay. Yeah. If you do Fibonacci numbers starting with 2 zeros, everything is 0. Anyway.
Uh-oh.
Yeah. It should work now. Yeah. I guess my thing isn't super smart because it's also recompiling the snake, but whatever. Anyway. Yeah, so now we have a basic working language, technically Turing complete, I think. Yeah, here, so you can see X is 55, which is the 10th Fibonacci number, or, well, if you start from 0, 1. Anyway, and yeah, so our language can do things now, but I want to make it better. So I'm just going to keep adding things basically until half an hour has passed. I have a bunch of things. I don't actually think I'm going to be able to get through everything, but we'll see. Anyway, so the first thing that actual programming languages have is like functions. So I wanted to define a function. I want to be able to define functions. So I'm going to call it fib of n, and then I put this in there, and I will return x, and n is going to be a parameter. So I want to be able to do this, and then I can say, result is fib of 10, like that. So to do this, we need to add a decent number of things, but it's not so bad. So first, of course, we're going to add the syntax for it. So we need to add function definitions. So define, ID is the name of the function. And then we have a list of arguments. So a list of arguments, I'm going to call it IDs, and I'll get back to that in a second. And then the body of the function is, again, statements. And then we also want return, return some expression. And we want to evaluate the expression. Actually, just do strict. I want to evaluate the expression before we return it, of course. And so any other syntax I need? Oh, function calls, yes. And I want to be able to call functions. So I want to do ID, name of the function, and then some list of expressions. And I want to evaluate the list of expressions before I call the function. Okay, so if I add this, I should be able to parse it, or whoops, I didn't do IDs or expressions. So K has this built-in list thing that you can use. It's list with commas. And I also want a list of IDs. IDs, list of IDs separated by commas. And yeah, basically it defines it so you can have like an empty list, or you have two lists of expressions concatenated by commas. The reason I didn't use it for this is because it doesn't really like it when you don't have a thing separating your items of your list. It's all weird, so anyway. Now, yeah, we should be able to parse the program, but it will of course not run. I didn't save the file, so yeah, it's still the old thing. Anyway, see, we have syntax now, yeah. So now we need to make everything work. So several steps of making things work, but the first step is building an environment of functions, or a map of names to functions that we can look up functions by. So to do that, I'm going to add a new thing to the configuration, call it defs. It's going to be another map, but this time mapping function names to function definitions. Ignore that for a second.
This is all runnable in IntelliJ, right?
IntelliJ. I've never done it that way.
Okay.
Probably. You probably run it from there.
Okay.
But I just, built it, and then it gives you a bunch of executable files in the bin directory, or kdistribution/bin. And that's what I'm using here. So I have this thing that just runs these commands every time we change the files, but the commands to run are compile, -s backend, whatever backend you want, then the file name, and then krun your program.
Okay.
Okay.
And SNK is like you like customize that, right?
Yeah, I mean, the extension doesn't actually matter. You can make it literally anything. Like you don't have to say like, SNK files are, associated to this language. I just did that.
All right.
Let's see, what was it doing? Oh yeah. So yeah, so the problem is it doesn't know whether this n here is a list of expressions or a list of IDs, because it could be both. So to handle this, I basically need to tell it that lists of IDs are lists of expressions. And while I'm at it, I'm also going to make lists of values, because a list of expressions evaluates to a list of values, or at least that's the easiest way to do it. So these things are all lists of expressions. And then K results are not just values, but also lists of values. Yeah, make sure I did everything right. Oh, I have this. I want struct on that. Okay. And then I'm going to put strict here so that if I have a list of expressions, every expression in the list of expressions will get evaluated. And K knows how to do that, just evaluates them one at a time. It doesn't have any particular order, but you can define order if you want using the strict annotation. Yeah, so now we parse the program correctly. We have this function definition, and then we have this assignment. Why does it think that's a list of IDs? Whatever. Anyway, so yes, back to the function environment. So I want to just take every function and stick it into our defs map. So we take some function with some arguments and some body, and we want to put it into defs. I'm just going to copy it in its entirety, even though having the name there twice is somewhat redundant, but it doesn't really matter. And then once we do that, we're done, and match the rest of the cell. Okay. So now when we run our program, we will have all the function definitions, I mean just one in this case, but all the function definitions in the defs cell, which makes it easy to look them up whenever we want to actually evaluate them. Okay. So next thing we need to do is actually evaluate them, because we're going to get stuck when we do result equals fib of this. And the way we want to evaluate the function is going to take another new configuration thing, configuration cell, to represent the call stack. This time I'm going to use a list instead of a map because I want it to be ordered. And yeah, dot list again is just an empty list, just like dot map is an empty map. And now the reason I want this is because I want to switch contexts essentially. So I'm evaluating the function in the function's context, as opposed to in the like global context. So to keep track of all these things, I'm going to create a new construct. So this also uses the syntax keyword, but it's not syntax of our language. It's just a thing that I want to be able to write in my language definition. And K item is just the sort of like all things, basically. So say I want to make something called call that stores a map, which is the old environment, and a K. K represents, so like this whole thing, including the sequencing arrows, is of sort K, because I'm going to want to store all the computation that will happen in the future so I can return to it after I'm done evaluating the function call. That maybe isn't clear right now, but hopefully will be once I show you the rule, or the couple of rules. Yeah, so rule. So when I do a function call, so I do f with some values. I'll make sure they're actually fully evaluated before I do the function call. When I do f with some values, what happens is I need to look up the function in the list of the definition map. So f maps to some definition with some arguments and some body. Defs, okay. And then what I need to do is evaluate, or I need to start evaluating the body now. But what I also need to do is pass in the arguments and switch evaluation context. So first I'm gonna, again, I'll define this in a second, but I'm gonna create a thing called setup args, which will take the args and the things I'm passing in. So the arguments being, in this case, n, and the thing I'm passing in being 10 is the VS. I'm going to create an auxiliary construct that will do that part for me. Then I will evaluate the body. And that will handle passing in the arguments. And the other thing I need to do is I want to save the current environment and the evaluation context to the call stack. So to grab the entire evaluation context, I'm just going to use the sequencing arrow and then K. This will match. So in this case, F is fib, VS is, well, it's this whole thing, and then K will be everything after the sequencing arrow, which is just one thing in this case, but it could be a bunch of stuff. And then I want to save this stuff and change the environment. So this old environment, I'm going to get rid of it because I don't want the variables to leak into my function call. And then I'm gonna update the call stack. So I have some list of calls. I'm gonna add a new list item to the beginning, which holds the environment and evaluation context. Call stack. Okay. So yeah, that one's pretty complicated. So if you have questions, let me know. I also need to find the setup args thing, which is going to be IDs and vowels. Okay. Yeah. I just defined setup. Okay. Anyway, so setup args basically needs to take each argument and each value and set them appropriately. So I'm just going to use this literally using the assignment we already have because that's the easiest way to do it. So the first case is when there's no arguments and no values, then I'm just done. And then the other case, of course, is when there are arguments. So some x, and then there's other x's and a value, some v and other v's. And then I just do x equals v. And then I set up the rest of the args like this. Okay, so when I run this now, you can see the set of args is here. It'll be evaluated, and in my environment, I will have just n equals 10. Then I'll run the body of the function, which should fully work, and then we'll get stuck at return because we just don't need to find what return means. Yes. So here we are. Yeah. So we want to return 55. So we need to find what return means, and the way we're going to do it, we need the call stack to remember what we were evaluating before we started evaluating this function. So using that, first I want to match on the call stack so I can get the call on the top of the call stack, which will have some environment in it, or some new environment in it, because we already have a current environment, and some new K that we're going to run now. Then we have the rest of the calls, and I will get rid of the first call off the call stack. Okay. And then, yeah, so I want to do this when we're doing return some value. And all we have to do is, because of course, if I return before the end of the function, I want to return then and not wait until the end of the function. So I'm going to take everything that comes after the return, and I'm just going to ignore it and get rid of it. So I'm going to just put underscore because I don't actually care what it is. And instead, I'm going to switch back to the context that I was called from, which is what this call stores. So in this case, you can see it's the assignment to result. And that's that. And then I also need to restore the environment. So whatever environment I had before, again, I don't care what it is. I'm just going to throw it away and go into this new environment. That should work. Let's see. Yeah. Does that make sense?
Wait, so I have a question about the call stack.
Yeah.
So you're adding uh the environment and the result to the stack, or I think I'm
Yeah.
misinterpreting it.
Yeah. So I'm adding the environment. K is okay. So when I do this, when I have a list of statements, I break it up into like sequencing one statement followed by a bunch of other statements. The
Yeah.
K is all the statements that are going to run after I do the function call. So I'm
I
saving,
see. Okay.
yeah, so I'm saving what's going to run after I do the function call so I can return to it after I'm done evaluating the function call.
Okay.
Yeah.
And then what is env?
Env is the like variable value map. So
I see. Okay, that makes sense.
yeah. So
Why do you need to return all of it instead of just the one they return? Why do you need the entire map?
Sorry, what do you mean?
Or what you env is the mapping between names and values, right? So it's like the value of every variable.
Yeah.
Pretty much.
Yeah.
So for the function, why would you need to return all the local variables instead of just the value that it returned?
Yeah. So I assume you're talking about this environment here, right?
Yeah.
Yeah. Okay. Yeah, so this environment is the environment that I had before I called the function. So I'm restoring the old environment. I'm not returning the environment from the function. So I'm
Oh, I
taking
see. Okay,
the
that makes
environment
sense.
that I was running in and overwriting it with this old environment. So I get my variables back.
Okay, that makes sense.
Okay, cool. Yeah, so now our program runs again. When we run it, we get result is 55, as expected. Yeah, so functions work. Hooray. So at this point, I'm just gonna add, I'm gonna keep adding things. Next thing I'm gonna add is for loops, because for loops are nice sometimes. So let's see, I want to have some statement here, semicolon, some expression, semicolon, some statement. Because what I want to write is statements. What I want to write is, instead of using this while loop, I'm just going to replace it with a for loop in the sort of standard way. I less than n. I don't have plus plus, so I'm going to do I plus 1. I could add plus plus, but I don't want to. It's not right now. Okay, so this code is obviously the same, but using a for loop instead. So let me save this file, and I'll know how to parse it, but not how to evaluate the for loop. So again, there's multiple ways you could implement this. I'm going to implement it in the sort of straightforward desugaring way, where you just take the for loop and make it into a while loop. So for the initializer, the condition, and the step, and then you have a body of the loop, and this will just become, first you do the initializer, then while the condition is true, you run the body, and then run the step statement. And that should be that. Hopefully that makes sense. Okay, cool. For loops. Other things that are nice. So in Python, for example, you can write x, y equals y, x plus y, like this, and it will work. So you don't have to have these temporary variables to do the swaps, which is nice. So I would like to add that to this language too. So I'm going to do that now. So instead of the assignment just being one variable, where is it? Yeah, so the assignment just being one variable equals one expression, I'm going to have it be a list of IDs equals a list of expressions. And now all I have to do is essentially recursively break this thing apart into a bunch of single assignments, which I've already defined. So let's see if I'm doing, so x, So if I'm doing x equals val, I'm done. I already defined that. If I'm doing x, y, and then other things equals v, w, and other things, and I want to make sure these are all values because I don't want to do this before it gets evaluated. Otherwise, I won't have the simultaneous effect that I want. And this will be x equals v, and then y x's equals w v's. And then I also need one case for when there's nothing on either side, just the base case, which is do nothing. So if I did everything right, this should work, and we'll have this multiple simultaneous assignment thing, which is kind of nice. No, I did something wrong. List terminator for overloaded term. Where is this? 47. Oh, I should tell it what this is. ID? Is that what it's telling me about? I guess I could actually read it and see. But it's okay. 47 is there. Why doesn't it make that? It doesn't have at least sort. Okay, what column is that? 14, yeah, right here. Maybe it doesn't. Or would it be vowels? Shouldn't matter. So 87. Okay, let me just try something. Okay. So this is exactly how I have the other one, but I don't think it should make a difference. Sorry. Okay, well, that works. Not really sure why that changed it. Oh, I see. Yeah, okay. Anyway, okay, so I think what it was yelling at me about is that, again, it couldn't tell whether something was a list, like what kind of list it was. In that, but actually it doesn't matter what kind of list it is, as long as it's a list. So yeah, even though before I had said, so okay, so before, let me get rid of this. Yeah, so before I had it like this and like this. So even though I said that a list of values is a list of expressions, they don't get literally parsed as the same thing. They get parsed as, you know, list of values versus a list of expressions, and then it's a list of values that is a list of expressions. This is probably a confusing explanation, but so the list of values gets parsed as like vowels and then like things, right? And the list of expressions gets parsed as expressions and things. And vowels things is an expression, list of expressions, but it's not literally the same term. So all I did by adding the k-label thing is I told it that there should be literally parsed as exactly the same thing and not just it's a sub sort. Hopefully that makes sense. If it doesn't make sense, I guess just write k-label and it'll work out. But yeah, sorry. Okay, so that's multiples.
With the way you implemented this, would you be able to do something like 0 equals 1 and then would 0 actually be set to 1?
That shouldn't work because the only thing on the left-hand side is IDs. I mean, I'll try it, but
Oh, I see. Okay, yeah, sorry, I thought it was an expression.
Yeah.
ID. Yeah, let's.
Yeah, and yeah, you can see over here that it works. Or the simultaneous assignment thing does what you expect, and we still get the same answer of 55. Let's see. Yeah, I had other things planned, but I was going to do generators, and that's definitely going to take more than 7 minutes. So maybe I'll
Oh,
just pause here.
I think I was. Oh, sorry. I think I was wondering about the simultaneous assignment. So is the simultaneous assignment assigning a list of IDs to a list of expressions, right? That's what it should be doing.
Yeah. Yeah.
Oh, I see. Okay, I misread something. Yeah, never mind. Sorry.
Okay.
I misunderstood something. Yeah.
Yeah.
No, makes sense. Okay.
Okay. Cool. Yeah. So that's the beginning of a programming language. Yeah, I'm just gonna stop here. You guys have any other questions, or actually 1 sec. Yeah. So I will put the sort of fully implemented version with the generator stuff up on this, or probably put it out on GitHub and then link it in the Slack. Yeah. You guys have any questions, comments, etc.? Okay, cool.
Yeah. Thanks for the presentation.
Yeah, sure. Let me see. We'll stop the recording.